So welcome all. In this lecture, we are going to learn about uniform plane wave propagation. So let the uniform plane wave propagating in z direction. So if the uniform plane wave is propagating in z direction, then there are two conditions associated with it. Talking about the condition number 1, if it is propagating in positive z direction, then the x and the y component will be present, but there is no z component. So z component will be absent. It implies that the electric field component, that is Ez, and the magnetic field component, that is Hz, will be equals to nothing but 0. So this is the condition number 1. Talking about the condition number 2, if the uniform plane wave is propagating in z direction, then there will be no variation in x and y direction. So the electric field intensity, that is E, and the magnetic field intensity, that is H, are independent of x and y. So this can be termed as del over del x of E is equals to del E over del y is equals to del H over del x is equals to del H over del y is equals to 0 only. Since it is propagating in the z direction, that's why there is no variation with respect to x and y direction, and all the components associated with x and y direction are being equals to 0 only. So these are the two major conditions that we gonna use in the upcoming derivation of the uniform plane wave in propagation. Since we all know that the general wave equation for the free space is given as del 2 E is equals to mu 0 epsilon 0 del 2E over del T square. This is the first general equation in free space, and in terms of magnetic field intensity, it is given as del 2H is equals to mu 0 epsilon 0 So these are the two equations associated with free space. Here E is nothing but electric field intensity, H is magnetic field intensity, epsilon 0 is permittivity for free space. And mu 0 is permeability of free space. let me give it as equation number 1 and it as equation number 2. So here is our equation number 1. Now here is the del square. So if we evaluate the del square, then its value will be equals to del 2 over del x square plus del 2 over del y square plus del 2 over del z square. And the vector representation for electric field intensity is given as E vector equals to Ex Ax cap plus Ey Ay cap plus Ez Az cap, where Ax, Ay and Az cap are nothing but the unit vector which are showing the directions only, and Ex, Ey and Ez are the component of electric field along x, y and z axis. Now if we put the values of del 2 and E in the equation number 1, then we will get first of all we will put the values in LHS. So putting the value of del 2, we get del 2 over del x square plus del 2 over del y square plus del 2 over del z square. Now in place of electric field intensity we write this expression. So Ex Ax cap plus Ey Ay cap plus Ez Az cap. Now we are done with LHS part. Now putting the values in RHS, we get mu 0 and epsilon 0 will be written as it is, mu 0 epsilon 0, and del 2 over del t square will also be written as it is. In place of electric field intensity, we write this vector expression. Ex Ax cap plus Ey Ay cap plus Ez Az cap. Since we know that our wave is propagating in z direction, thus according to the two conditions that we discussed, the electric field component along the z direction will be equals to 0, and also there will be no variation in x and y direction. That's why del over del x is equals to 0 and del over del y will also be equals to 0. These are the conditions that we discussed earlier. Applying these conditions in this expression, we get our modified expression as here, since del over del x is equals to 0, so del 2 over del x square will also become 0, and del 2 over del y square is also become 0 because del over del y is 0. So the remaining term is del 2 over del z square. And Ex Ax cap can be written as it is plus Ey Ay cap can be written, and now here is Ez. Since Ez is equals to 0, that's why this term will become 0 only. Is equals to mu 0 epsilon 0 del 2 over del t square Ex Ax cap plus Ey Ay cap and since Ez is equals to 0 only, that's why we ignore this term. So this is the modified expression. Now on multiplying it inside the bracket, we get del 2 over del z square of Ex Ax cap plus del 2 over del z square of Ey Ay cap is equals to mu 0 epsilon 0. On taking del 2 over del t square inside the bracket, we get del 2 over del t square of Ex Ax cap plus del 2 over del t square of Ey Ay cap. Now on comparing the component or the coefficients of Ax cap and Ax cap and Ay cap and Ay cap, we get, on comparing the coefficient of Ax cap, firstly we get del 2 over del z square of E of x will be equals to mu 0 epsilon 0 of del 2 over del t square E of x. So this is equation number 3rd. And on comparing the coefficient of Ay cap on both sides, we get del 2 over del z square of Ey is equals to mu 0 epsilon 0 del 2 over del t square of Ey. So this is our equation number 4th. Now similarly we do the whole procedure that we did for the electric field intensity also for the magnetic field intensity. So this is the general wave equation that is represented as equation number 2. Now here is the del 2 or del square, that can also be written as del 2 over del x square plus del 2 over del y square plus del 2 over del z square. And now if we talk about the vector representation of this magnetic field intensity, then it can be written as Hx Ax cap plus Hy Ay cap plus Hz Az cap. If we substitute these both values in the above expression, then we get, in place of del 2 we firstly write this expression, that is del 2 over del x square plus del 2 over del y square plus del 2 over del z square. And in terms of magnetic field intensity, we write this expression Hx Ax cap plus Hy Ay cap plus Hz Az cap will be equals to mu 0 epsilon 0 del 2 over del t square in place of magnetic field intensity we write this expression, that is Hx Ax cap plus Hy Ay cap plus Hz Az cap. Now we know that a wave is propagating in z direction. Since wave is propagating in z direction, That's why we can say that the magnetic field component along the z direction will be equals to 0, and also del over del x will be equals to 0, and del over del y will also be equals to 0. Applying these three conditions in the above expression, we get our modified expression as, since del 2 over del x square is equals to 0, del 2 over del y square is equals to 0, so the remaining term is del 2 over del z square. And here hx ax cap plus hy ay cap and hz is equals to 0 equals to mu 0 epsilon 0 del 2 over del t square hx ax cap plus hy ay cap, and hz is equals to 0 only. Now on taking this del 2 over del z square inside the bracket, we get del 2 h of x over del z square ax cap plus del 2 over del z square hy ay cap is equals to mu 0 epsilon 0 del 2 over del t square of h of x ax cap plus del 2 over del t square of h of y ay cap. Now similarly we will compare the coefficient of ax cap and ay cap. So firstly, on comparing the coefficient of ax cap and ax cap from both the LHS and RHS, we get del 2 h of x over del z square is equals to mu 0 epsilon 0 del 2 over del t square of h of x. So this is equation number 5, and on comparing the coefficient of ay cap, we get del 2 over del z square of h of y is equals to mu 0 epsilon 0 del 2 over del t square of h of y. This is equation number 6. Now we can say that equation number 3rd, 4th, 5th and 6th are the differential equations of second order. And the general solution for such differential equations are it is given as E, that is being equals to F1 Z minus C of t plus F2 Z plus C of t. So this is the general solution for these differential equations. Here f1 and f2 are the function of z minus ct and z plus ct, and here f1 z minus c of t represents the wave traveling in positive z direction. Represents wave traveling in positive z direction, and this f2 z plus c of t represents wave traveling in negative z direction. And here c is nothing but velocity of electromagnetic wave, that is also equals to the velocity of light. Now let us have a look at a case. According to this case, if there is no reflecting surface, since the reflective surface is not present, that's why the movement of the wave that is traveling in negative of the z direction is not possible, because the wave is not reflecting back. So that's why the second term, that is representing the wave traveling in negative of z direction, becomes 0. So f2 z plus ct will get 0. Now the general solution of the wave equation will become E, that is being equals to f1 z minus ct. So this is general solution of wave equation. Thank you. If you like my videos, then do subscribe my channel and press the like button.